Hello, BNG319 class. This is the second part of the organic chemistry reactions section. We're finishing off organic chemistry reactions week here in BNG319. If you have any questions regarding what you have watched for these two lectures, please feel free to send me an email asking for some more details if you want them. And my plan is going to be to host a not a review session necessarily, but a recitation session, a voluntary recitation. I did this last year; was quite successful. So I'll probably host one of those on Monday at some point in Textiles 219. If that is something you want to attend, please send me an email and let me know what times you're available. I'll try to accommodate everyone. I can't promise that I'll be able to do that if there's a lot of people, but I'll do my best. But for now, let's go through the remainder of the chemical reactions that we're going to talk about this week and see how we're doing with those, and also go over some points from last time. Okay, so from last time, we had talked briefly, we started off talking about isomers of alkenes, and those come in two flavors, cis and trans, and you can think about cis and trans isomers based on this little graphic here, where we're looking at 1,2-dichloroethene, where a trans isomer, trans across is meaning across, and you see the double bond here in yellow, and the two carbons, and relative to the double bond, where are positioned the two molecules, the asymmetric molecules. You've got hydrogens, but in this case we're talking about chlorines. Last time we talked about methyl and ethyl groups. So where do the chlorines position themselves in these 1,2-dichloroethene molecules relative to the double bond? So you got one above and one below, and that is the definition of a trans isomer. So this is trans 1,2-dichloroethene. If both chlorine molecules are on one side, in this case they're on the top relative to the double bond. If they're on the bottom relative to the double bond, it would be the same thing. If they're on both on the same side, they are the cis isomers. This would be cis 1,2-dichloroethene. So these are what are known as geometric isomers. These are compounds that have different spatial arrangements of groups attached to the carbons of a double bond here. And it's helpful to note, and we talked about this last time, there must be two different groups, so there must be a certain amount of asymmetry on each carbon of the double bond. Okay, so we can think about this in terms of cis or trans here, these isomers. So the molecule here is called 2-methyl-2-butene. And the question is this cis, trans, or neither? Okay, so looking here, I see symmetry on this one carbon, saying to me that, okay, well, this is probably neither, because we could argue, okay, it's cis if we're looking at the top carbon here, it's trans if we're looking at the top carbon here, but it's cis if we're looking at the bottom carbon here. So if this was a hydrogen, this bottom carbon was hydrogen, like this hydrogen, we would have a trans molecule. If this was a hydrogen instead of a methyl group, we would have a cis. But in this case, we have neither. And so the answer is that it is neither cis nor trans, because there isn't that heterogeneity here on this one carbon that's attached to the double bond here. So it's neither cis nor trans. And again, let's go over it again. Why is it neither cis nor trans? Because there's a methyl group here and a methyl group here. There is too much symmetry for us to be able to make that distinction. Okay, and again, we talked about for both radical reactions and for carbocation reactions, what forms or what intermediates are more stable. And this is going to affect what products we see in reactions with these types of intermediates. So in this case, we're talking about a radical reaction here. The more highly substituted radicals, so this methyl radical here is less stable than this radical, this ethyl radical, which is less stable than this radical here, which is less stable than this. So this is the most stable because the carbon that has the radical is substituted, the carbon-hydrogen bonds are substituted with carbon-carbon bonds. So what we mean by highly substituted is indeed that the carbon-hydrogen bonds are substituted by carbon-carbon bonds. So the more stable they are, so the more highly substituted they are, the more likely they are to form product. The more likely the stable radicals, the stable carbocations are going to be to form a product. And that's where we get what is the major and what is the minor product. You can always know the major product because the product will have the substitution on the, or will have the reaction will occur on the more highly substituted carbon. And we looked at this when we talked about halogenation of alkanes, which is a radical reaction. It started by making chloride radicals by hitting chlorine with light, or bromide radicals hitting bromine with light, and those radicals will start the chain reaction that will cause these products to be made. So we ask ourselves, which are the major products of these two reactions here? What we're actually asking, or also what we're asking, is which is the product with the halogen on the more substituted carbon. That's essentially what it means to be the major product here. So we can look and say, well, the more, in general, to start off, the more substituted carbon is this middle carbon right here of this propane. So where is the chlorine going to end up? It's not as likely to end up on the end here, which is a less substituted carbon. It will happen, but it won't be the major product. The major product will be here in carbon number 2, where a hydrogen will be exchanged for a chlorine, and we'll get 2-chloromethane right here. So this is going to be the major product right here. This species right here. And here we've got butane, and we're going to hit bromine with some light and brominate butane, which is the more major product. Again, we ask ourselves which has the halogen on the more substituted carbon. It's not this one with the halogen on the end, it's this one that has halogen in the middle. So there'd be 2-bromobutane here, and it would be the major product of this reaction. And so radical reactions, we think of alkanes as being fairly unreactive, and in fact, it takes something incredibly reactive in order to make an alkane a reactant in a chemical reaction here. So these radical reactions are initiated, which is the making of the initial radical, and these are the chloride radicals here. Again, we're hitting, if we got chlorine as one of the participants in the reaction, we have chlorine to start with, dichlorine. We hit it with light, which breaks that bond and creates a radical. Creates 2 radicals, to be precise. So it has initiated these substitution reactions. So now we got chloride radicals, and then we're going to have propagation, and the first part of that is radicals making more radicals. So chloride is going to turn this propane molecule into a propane radical, a 2-propane radical here. So now we have a radical here that is ready to react with something else now. This unpaired electron really wants to pair. We could also, and we will get to a certain extent, this happening on the end as well, on the less substituted carbon. But in general, the propagation is going to occur like this, with the radical being made on the middle carbon of this propane molecule. And next, with propagation, is radicals making products. So here we have the radical being made, propane radical here. Now we have a propane radical. We've got chlorine. So this radical wants to pair with an electron. Well, it's going to break apart this dichlorine here and then share the electrons, and we're going to end up with 2-chloropropane as the product, as our major product. We still have a chloride radical, so what happens to that? Well, eventually termination will occur, and chloride radicals will react with each other and become dichlorine again. No more radicals, no more reactions. So once all we have is dichlorine and the 2-chloropropane, we won't have any more reactions because all the radicals will be gone in this reaction mixture. Now the question you might have is, so we talked also about nucleophiles and electrophiles. Are all nucleophiles radicals? Well, the answer to that is no. That is not the case. In fact, what's more common is ions as nucleophiles in a reaction. And also it depends on the element or elements and compounds that are involved in any given reaction. So, it depends on whether we have halogens, nitrogen-containing compounds, an alcohol group, a sulfhydryl group, etc. But we will talk a lot more about nucleophiles and electrophiles as we get into our organic chemistry here. Okay, so what I've been showing you these past couple times here, a bunch of reactions with a bunch of arrows and things like that. And what does all this mean? Well, let's kind of go over that because we're going to be going more in depth into reaction mechanisms very soon here. So it really helps to know what's happening. So what do the arrows mean? Well, they illustrate movement of electrons in a given synthetic step. So, for example, if we're looking at one-headed arrows like we have been with the radical reactions, well, that represents movements of a single electron. And you can see right here in this illustration here that the chloride radical, well, you've got the single reactive electron here. So it's going to move that electron, and an electron from the hydrogen is going to move, and they're going to pair with each other to make HCl. And this hydrogen is going to donate one electron here to make the methyl radical. So that's what's happening in this situation here. So we're seeing, in this radical reaction, we're seeing movement of single electrons here. But typically, if we're not looking at radicals, you'll see mostly two-headed arrows, and that represents the movements of one pair of electrons. So this ammonia is donating this pair of electrons to the hydrogen to make this ammonium ion, and then the hydrogen here is donating a pair of electrons to the oxygen to make the hydroxide ion. Okay, so back to our chemical compounds here. We have alcohols, and these are important compounds, important molecules in organic reactions. Carbon-containing molecules that have a hydroxyl group attached, that OH at the end, like ethanol and N-butanol. And they're bound to a saturated carbon atom here. And so a lot of common alcohols like ethanol, isobutanol, and N-butanol are in this category. And we'll see more of them as we go on here. Alcohols, just like carboxylic acids, can hydrogen bond to each other. They can be hydrogen bond donors, and they can be hydrogen bond acceptors. With this hydrogen here, that can be a donor of hydrogen bonds. With the oxygen here, that can be acceptors. And so again, I've been saying donor and acceptor when talking about hydrogen bonding. So what does that mean? What am I saying here? So the donor in a hydrogen bond is the hydrogen, which is connected to an electronegative atom. like nitrogen, oxygen, and you'll see nitrogen and oxygen most often in organic reactions that we talk about here, or fluorine atom. Fluorine atom could also have a hydrogen that is a hydrogen bond donor, like hydrofluoric acid. And an acceptor is the electronegative atom with a free lone pair. So again, this could be the oxygen, the nitrogen, could be a halogen perhaps. So that would be the acceptor. But the donor is always a hydrogen, and the acceptor will be an atom that has a free lone pair of electrons. And remember that oxygen and nitrogen certainly fit that bill, even if you don't see the full Lowry write out of the molecule here. Like they're not showing the entire the unpaired electrons in the oxygens here in this example. So these hydrogen bondings are relatively strong in terms of being fairly nonspecific. Relatively strong intermolecular force that helps explain melting points, boiling points, gas behavior, and much more. So in terms of other intermolecular forces like van der Waals forces, hydrogen bonds are fairly strong. And we see them a lot in biochemistry, in organic chemistry, and in biology. They hold our DNA strands together, for example. So hydrogen bonding is very important, and we are going to see hydrogen bonding and deal with it throughout pretty much the remainder of this course here. Okay, one question. Which of these compounds below can form hydrogen bonds with molecules of the same type? So this is a good question here. Which can form molecules of this hydrogen bonds with molecules of the same type? So they have to be both a hydrogen bond donor and a hydrogen bond acceptor at the same time. And so which ones can do that? Well, water we know can do this. It's got the HO bonds. The H can be a donor and the O can be an acceptor. So certainly water can make hydrogen bonds with molecules of the same type. Same with ethanol here. We've got H to act as donor, and we've got the O to act as acceptor of hydrogen bonds. This acid here, acetic acid, has the OH. The H can be the donor. Either one of these oxygens can be an acceptor. We have this ketone molecule here, and what we see is that, okay, the oxygen certainly can act as an acceptor, but we really don't have an H attached to an electronegative atom to allow for a hydrogen bond donor. So the only one that cannot, as a matter of fact, form hydrogen bonds with a molecule of the same type is this ketone here. And so it's pretty much everything except B is the answer for this. And now, as we're talking about hydrogen bonding and what it affects, we ask ourselves which boiling point is higher for these two molecules here. So which molecule has the higher boiling point? Obviously you can see this was supposed to be a Socrative question. The molecule A, which is this cyclohexanol here, or methyl cyclohexane here, molecule B. And so one of the hallmarks, and this is what makes water so interesting, with all those hydrogen bonds, it has a fairly high boiling point for what it is. So one could imagine that with the ability to make hydrogen bonds and to act as a hydrogen bond donor or acceptor, that maybe molecule A, cyclohexanol, has the higher boiling point. And let's see which one it is. Indeed, it is the cyclohexanol, molecule A. Why? We talked about this just now. Because it has the ability to hydrogen bond with itself. So it has the hydrogen here attached to the oxygen. The hydrogen can be a hydrogen bond donor. The oxygen can be a hydrogen bond acceptor. So it can form hydrogen bonds in solution, which will raise the boiling point of the molecule in solution. A solution of cyclohexanol will have a higher boiling point than, say, a solution of methyl cyclohexane. So what kind of reactions can we do with alcohols? We know they're good at hydrogen bonding. Well, what sort of reactions can happen? So we can get oxidation of alcohols, and if you recall, oxidation in organic compounds, we can start by thinking of oxidation as the addition of more carbon-oxygen bonds. And so that's what we're seeing here in this these oxidation reactions here with these alcohols. So potassium dichromate is the oxidizing agent. It is not a catalyst, because potassium dichromate is altered in these reactions here. So we have potassium dichromate modifying a primary alcohol, oxidizing it to form an aldehyde. We go from one carbon-oxygen bond to two carbon-oxygen bonds here with this carbonyl group right here. We can oxidize it even further to go from these two carbon-oxygen bonds in the aldehyde to 3 in the carboxylic acid. And so this is as oxidized as it's going to get. If we have a secondary alcohol, we can oxidize that to a ketone. We now have 2 carbon-oxygen bonds, and that's as far as we can go with that. If we were to try to add potassium dichromate to a tertiary alcohol here, we would get no reaction, because we can't possibly oxidize it any further because it's too highly substituted. The carbon does not have a hydrogen to give up. It only has carbon-carbon bonds, as well as the carbon-oxygen bond here. So we can't possibly get a carbonyl group out of this. So you wouldn't see any reaction at all. You'd end up with potassium dichromate swimming in a pool of tertiary alcohol. We can get dehydration of alcohols. We talked about hydration of alkenes, and this is dehydration of alcohols here. So if we have an acid catalyst and we have heat, alcohols can be dehydrated. And we've gone over already dehydration reactions, but they bear going over again. So we can go from alcohol to alkene. So you look here at 2-butanol, we add acid and heat, we end up with 2-butene plus water. And again, you consider the major product of the reaction dictated by Markovnikov's rule. So basically, what kind of alkene would we make? Would we make 1-butene? No. By Markovnikov's rule, we're making 2-butene here. And that's what we get. Because again, it's all about the substituted carbons here. Okay, so again, what is the product here? This reaction here, this looks like it's going to be an oxidation of an alcohol to make an alkene. What is the major product of this reaction? Again, as you can see, this is supposed to be a Socrative question. This is 3-methyl-2-pentanol. We add acid and heat to it. So do we get product A, product B, C, or D? So essentially, this product A it's got the double bond. We're removing an alcohol. Would the double bond end up being on the 5th carbon and the 4th carbon here? Well, we've already talked about Markovnikov's rule applying, so this would be in violation of that. So this is probably not what the major product is going to be. Although we might get some of this in the reaction, but the major product is what we're looking for here. This is, again, the alkene is between 1 and 2, but if you see the symmetry, we can flip this over and it looks the same as A. Okay? And given what we said about Markovnikov's rule, it's not C anyway, but C is essentially the same thing as A. So neither A nor C are our man here, our compound. D, well, there's no way this would happen at all because the OH is not on this carbon here, and it wouldn't be the major product if it was anyway. So D is out, so it must be B. B must be our major product, and you can tell here because in this structure here of 3-methyl-2-pentanol, we have highlighted the H and the OH that are going to get removed in this dehydration in blue. So you know these guys are going to get removed, and what we're going to be left with is a double bond right here, and so that's our answer. And so 3-methyl-2-pentene is our major product here. And again, you want to use your clues here when presented with, okay, I've got alcohols and I've got reactions. What's going on here? Is the alcohol being oxidized? Is it being dehydrated? I have no idea. But what else is involved in the reaction? If you see potassium dichromate involved in the reaction, you stop and say, okay, I've got an alcohol, potassium dichromate, aha, that's an oxidation. So basically I'll turn this OH into a carbonyl oxygen here, C double bond O, as an oxidation reaction. If you see acid and heat, and these are catalysts, you can think to yourself, okay, this is an alcohol, well this must be a dehydration reaction. Okay? So when confronted with this on a quiz or an exam or something like that, look at the entirety of the reaction, not just the main organic compound that's going on here. So if I see, potassium dichromate, I know what to do. If I see acid and heat, I know what to do. I know which reaction is which. Okay, let's talk a bit about sulfur-containing compounds. We have thiols. These are molecules that have a terminal SH. So like ethyl mercaptan here, we've made ethyl mercaptan from ethyl chloride in this reaction right down below. Sulfides are molecules that have a carbon-sulfur-carbon linkage. Disulfides, and these are common in proteins, these are molecules that have a CSSC, a carbon-sulfur-sulfur-carbon linkage, and these are formed from sulfhydryls here, this sulfur-sulfur bond here. And so again, this is a synthesis using ethyl chloride to make ethyl mercaptan. So that is partially what the synthesis of a thiol would look like. We can then oxidize thiols, and that results in disulfides. So we have two molecules of ethane thiol. We add some iodine to the reaction, and that will give us this oxidation product, this diethyl sulfide. And we end up with some protons and some iodide ions. And again, you can use your clues in regards to what's happening to the iodine here. Well, we see that the iodine is gaining electrons, is going from iodine 0 to iodine negative. So, in essence, you know that this is an oxidation reduction reaction. A question about the products. Why are we looking at, as the products, two molecules of proton, hydrogen ion, and 2 molecules of iodide ion? Why don't we just have 2 hydroiodic acid? And the reason for that is that hydroiodic acid is a strong acid, and its conjugate base, the iodide, is weak, and it does not want to form HI. So we don't want to form hydroiodic acid in solution because iodide is such a weak conjugate base. So we won't see H plus and I minus forming HI in this case. Molecules containing a carbon-oxygen-carbon linkage are called ethers. They can be synthesized like alcohols and thiols. And again, we have this alkyl moiety right here. We have a halide like methyl bromide. The reaction occurs, we get dimethyl ether. As you can see, we have a carbon-oxygen-carbon linkage, and the bromide ion is kicked out. And this again brings up what a leaving group is. So if you learn anything from this, know what are the electron donors, what are the electron acceptors, and what are the leaving groups when we talk about nucleophilic substitution here. These are nucleophilic substitution reactions, and an atom or a group of atoms that is displaced from a molecule is the leaving group. So in this case we have iodide. It is donating electrons to this carbon, which then the bond donates these electrons to the chlorine to form a chloride ion, and we get a substitution, this iodine, for this chlorine here. So we started with sodium iodide, we end up with sodium chloride. And just how good a leaving group is varies depending on how good a conjugate base that species is. But in general, halides are good leaving groups. Okay, aldehydes and ketones. These are C double bond O. They have the carbonyl carbon. The aldehydes contain it at the end of the carbon skeleton. So you see C double bond O with an H at the end here, like formaldehyde. Ketones also have that carbonyl group, the carbonyl carbon here, but it's in the middle of the molecule. And ketones thus are not as reactive as aldehydes. Acetone is fairly stable for an organic molecule, for an organic liquid. So acetone is a ketone, whereas acetaldehyde is not as stable, for sure. And the difference is in the placement of the carbonyl carbon. So here are some aldehydes and ketones. Methanal is an aldehyde. It's also called formaldehyde. Ethanal is acetaldehyde. Methylpropanal is another aldehyde. Propanone, otherwise known as dimethyl ketone or acetone. 2-pentanone is methylpropyl ketone. 2-methyl-3-heptanone is a butyl isopropyl ketone here. And what are the reactions that can be formed here? We can form what is called an acetal or a hemiacetal here if we have a reaction with aldehydes and ketones here. So we have here an aldehyde and an alcohol. And the reaction that occurs, and again it's a nucleophilic substitution, we end up with a hemiacetal here. And now we have this same hemiacetal, we react with another alcohol. We get a full acetal. And the hallmark of an acetal, as we'll go into in a bit, is the carbon-oxygen-carbon-oxygen-carbon linkages. So you can see we can react an aldehyde with an alcohol to get a hemiacetal. We can react that hemiacetal with another alcohol to get a full acetal. And we can look at the mechanism of this, where we have, here's our aldehyde, here's our alcohol. So we see the unpaired electron, or the free electrons in the oxygen will donate to this hydrogen, and then this bond donates the electrons to the oxygen. We end up with a double bond OH. The bond donates the electrons back to the oxygen. The electrons in the alcohol donates to the carbon right here, the carbonyl carbon, and then we get the water comes back. The water that we made up here comes back, and these electrons donate to the hydrogen, pulling that off and remaking that acid, the H3O+, and here is our acetal. Okay, one thing we have not gone over yet is resonance, and I have mentioned to you a few times about the aromatic compounds that have these that have these conjugated double bonds here. What does that mean? Why do we care? Because of this resonance, they have some important properties here. So here's phenol, has a pKa of about 10. It's much more acidic than cyclohexanol, which is a pKa of 16. And why is that? Well, the conjugate base of phenol is better able to stabilize the negative charge here. And what is and so that's down to resonance. So benzene or any phenyl group is called a resonance structure for the reason that the electrons or bonds that are shared among the 6 carbons in the ring. So you will see, like for example, benzene here, you'll see the bonds are kind of shared by all 6 of these carbons here. So there's not necessarily this double bond, single bond, double bond, single bond, double bond, single bond. It's kind of shared all over. You can write it like it is here, where you have an arrow, double-headed arrow going between this structure and this structure. More accurately, and a lot of people do this, we show benzene and aromatic 6-carbon rings with a hexagon that has a circle inside, and that really is more to the point of chemically what is going on, where we have the 6 carbons sharing the electrons / bonds. Not necessarily that the bonds oscillate like would be here. So this is a little more accurate to say that here. And that's resonance. And that's what is going on in these benzene and other phenyl structures here. So the conjugate base of cyclohexanol, the ion here, has a negative charge on the oxygen. The conjugate base of phenol is able to spread out that negative charge because of that sharing over the multiple atoms. So we have the conjugate base here. Electrons can be donated and donated again, and moving the double bond about. The double bond can be a carbonyl group here, and here's the negative charge, or it can do it on the other side and have the negative charge there as well. So it can just go, it can be distributed over pretty much the entire molecule, this negative charge in the conjugate base of phenol. So it's a more stable conjugate base in terms of the cyclohexanol. So it's a better acid here. So resonance, the double-sided arrow indicates different resonance forms, and each picture illustrates contributions to the overall picture. So these are all contributions. It's not necessarily an overall snapshot, which is why also it's more accurate to draw the aromatic ring like this in terms of what is chemically going on than showing this. We don't have a snapshot of sometimes the bonds are here, another snapshot, sometimes the bonds are here. Basically, it's a big sharing. And that's the same with the conjugate base of phenol here. It's distributing the negative charge because of this sharing. So it's not just passing it around like a hot potato. It is actually sharing this. So that's what's going on. It's just the contribution is shown in this way, where we have the double-sided arrow showing the resonance forms, not really donation of the electrons here. Okay, so we can think about this. Acetic acid is significantly more acidic than ethanol. Why is that? Well, the conjugate base of acetic acid is resonance stabilized. Just like the conjugate base of phenol is resonance stabilized compared to the conjugate base of cyclohexanol. So again, you can see this stabilization here. And again, this is showing not necessarily a snapshot, but it's kind of showing how the negative charge is distributed between these two oxygens here. And oftentimes you will see a kind of a dotted line that extends from this oxygen all the way to this oxygen, and that kind of indicates the resonance stabilization in, say in this case, acetate. Okay, so let's bring it back to something we talked about earlier when we talked about antioxidants. Vitamin C is an antioxidant that everybody's heard of. And again, the reason antioxidants are what they are is that they stabilize these free radicals by this resonance. So much like what happens with conjugate bases, these radicals of vitamin C and other conjugated double bond molecules are stabilized by the fact that they have resonance, a sharing of electrons. They're much less reactive than, say, this chloride radical here. So we get HCl plus the vitamin C radical. The vitamin C radical can be resonance stabilized, again, not necessarily tossing the radical around like a hot potato, but just sharing in that stabilization and decreasing the reactivity of this radical here. Okay, so we've talked a lot about what we'd say are inorganic mechanisms, organic mechanisms. So a lot of the nucleophilic substitutions that we've talked about are more or less organic in terms of the mechanism. But there are some reactions that have inorganic mechanisms, like reductions of aldehydes and ketones, oxidation of aldehydes, oxidation of alcohols and thiols. And again, a reminder as to what oxidation and reduction are. They are lost electrons for oxidization. Reduction is gained electrons. So if in the context of organic chemistry, oftentimes oxidation is just the addition of a carbon-oxygen bond. Reduction, it often takes the form of the addition of a carbon-hydrogen bond as compared to a carbon-oxygen bond. So both alcohols and aldehydes can be oxidized by strong oxidants like our dichromate ion here. So you can see here's an aldehyde. With some dichromate we can make an acid. We have an alcohol on one end of this molecule, an aldehyde on the other. We hit it with a bunch of dichromate, we get a diacid. We have an aldehyde and an alcohol in this molecule. We get a carbonyl group in the middle, and we get an acid on the end. Okay, certain oxidizing agents can oxidize aldehydes while not touching alcohols. One good example, and we'll talk more about this when we talk about sugars, is the Benedict's reagent. So this contains copper 2+, as our oxidizing agent. So here we have an aldehyde, and here we've made, with oxidizing by copper 2+, we have made an acid, or at least in this case, an acetate molecule. Here's another aldehyde, and here's an alcohol on the other, and you can see the alcohol stays the same, but we have over here a deprotonated acid here on this side because of the oxidation with copper. Same here, we have an alcohol and an aldehyde. We end up with, again, the deprotonated acid, but the alcohol is still an alcohol. And Benedict's reagent is such a thing that we can visualize the oxidation that's going on. So we add Benedict's reagent to oxidize aldehydes, which results in a color change of the solution here. So you can see, you have the blue color, which means the reaction did not happen, and we get varying between green and orange, tells us that Benedict's reagent has done its job. And reduction of aldehydes and ketones. So just like with alkenes, aldehydes and ketones can be reduced with hydrogen in the presence of a catalyst. In this case, we're talking about platinum here. So, and we'll talk more about the mechanism of this and the catalyst itself in a future lecture. So we have formaldehyde with hydrogen, and we can make methyl alcohol here. Acetone, we add hydrogen in the presence of a platinum catalyst, we make isopropyl alcohol. here. And the blue indicates where the hydrogens have ended up in this molecule. So we can provide the product for the following reactions here. So here is, we have a carbonyl, and we have a hydroxide here, or hydroxyl. And what are we going to do? We are reducing this carbonyl here, most likely. We can't really reduce the hydroxide much more. So we end up with a dialcohol here, because we have reduced this carbonyl to a COH. Here we have an aldehyde. We want to reduce that to make an alcohol. Okay? So it's taken the C double bond O and made COH out of it. Here we have two carbonyls, an aldehyde and a ketone group. We can then end up with a diol, because both of these will get reduced. Although I will point out that this is not a balanced reaction. We would have this molecule plus 2H2 here if we really wanted to reduce both of these carbonyl groups to alcohols. Thiols can be oxidized, and we've shown this already with iodine being one of the oxidizing agents. So what is iodine? It's being reduced, so it is an oxidizing agent. You can tell iodine is being reduced because it's going from iodine 0 to iodine minus, right? Because it's gained electrons. It's an oxidizing agent. It's being reduced. It's capable of carrying out this disulfide bond formation, which is the oxidation of thiols. So disulfides then can be reduced back into thiols, and this can be done with certain reducing agents. And this is done in cells with dedicated reducing agent type proteins and cofactors, but it can happen with this interesting molecule right here to form, again, the different thiols here from this disulfide. Okay, so overall we've gone over a bunch of the classes of molecules that we were first introduced to back last week. Alkanes, alkenes, alkynes, all aliphatics, alcohols, aldehydes, ketones, carboxylic acids, thiols, halides, and some amines as well here. We've talked about some reactions. First we talked about radical reactions, the halogenation of alkanes. We've talked about nucleophilic substitution. We've gone over what are nucleophiles and what are electrophiles. We will go over it much more as we go on here. And again, we've come back to oxidation and reduction. In fact, we just talked about that. And so we'll keep those in mind. We've talked about some structural things, especially hydrogen bonding, which is important, again, for the remainder of the class. And we've talked about resonance, and we will, again, talk more about resonance later on. Okay, so as a reminder, you can read chapters 8 and 9 here. This particular lecture is mostly chapter 9. Note that homework 1 is coming up. It's due next Tuesday when I get back. I'm giving you another assignment here, which will be the Tuesday after next. Again, this is end of chapter questions for chapter 8 and chapter 9. And I would like to have a Monday voluntary recitation on Monday, the October 2nd, before the quiz. So if you are interested in that, please shoot me an email with all haste and let me know what times you're available, and then hopefully we can put something together, and I'll meet everyone in Textiles 219 that day, and I'll answer any question you have. Okay, well, hopefully your week has been good, and I will see you all soon.